Good day, everyone. This is my first capstone, and for this capstone, I'll be using the supervised learning algorithm decision tree in order to classify whether a patient using their brain MRI exam results has Alzheimer's disease or not. So first things first, I've imported all of my libraries that I've needed for this project, and my dataset came from Kaggle, in which it consists of the 150 subjects, age from 60 to 96, in which each subject was scanned at least once, and everyone is right-handed. 72, in which also 72 of the subjects were grouped as non-demented throughout the study, in which, and the other 64 were grouped as demented at the time of their initial visits and were considered throughout such show for the rest of the study, and 14 subjects were considered non-demented at the initial visit and were later characterized as demented at a later visit. So my dataset consists of 15 columns, in which I'd be only using or dropping a few columns, in which I don't need the MRI ID, and I'm only going to be using the first visit for this analysis. I'm also dropping the hand column since all of the subjects are right-handed. So after I've read into the notebook my dataset, I've put my random seed to be 5 to ensure that any randomness throughout the code will be consistent. And I've then pre-processed my dataset. So for this analysis, I'm only going to be keeping the first visit only. I've then changed the categorical columns and gave it numerical values. So for this, I've only have to use or only do that for the gender columns and the group columns. So I've replaced female to be 0 and male give it a numerical value of 1. I have also converted my group column where I've classified given demented a value of 1 and non-demented a value of 0. After that, I've dropped all of the columns that I don't need for this analysis. So here is the resulting dataset that I have left with, in which I've only have the subject ID, the group column, which are now consist of 0 and 1, 0 being non-demented and 1 being demented, the gender column, in which I've given males 1 and females 0, and the rest as it was in the original set. I've also set the subject ID to be the index of this dataset. So I've decided to create some visualizations to see some relationships and trends in my dataset. And one of this that I want to see is the demented rate based on gender. So what I did was to create a stack vertical bar for this. And here is the result. So you can see, or this plot shows us that male patients are mostly composed of demented patients, hence they're more likely to have dementia than females. And it also shows that there is a higher number of women that are considered non-demented compared to men. I've also made a line chart to see the relationship between age and dementia rate, and you can see here that the non-demented group, as seen by the red line, has a lower concentration of 70 to 80 years old, while the demented group have a high concentration of that age range. We can also see in this visualization of the years of education and dementia rate that patients who were grouped as demented have a lower number of years of education compared to the non-demented group. And last of my visualization, we can see that the non-demented group has a higher test result in the mini mental state examination compared to the demented group. So for this plot, we can see that men are more likely to be demented than women. Demented patients were less educated in terms of years of education, and that there's a higher concentration of 70 to 80 years old in the demented group than those that are in the non-demented group. So furthermore, into my data processing, I've checked any missing values for each column, and we can see that the group column SES has 8 rows that have a missing value. In order to resolve this, I've used the median of the SES column for each group of unique values in the years of education column. And I've used median because the SES column is consist of distinct values. So after I filled any missing values in the SES column of the median, grouped by the education years of education column, I can see here that there are no more missing values in the dataset. So after that, I've gathered all the labels is the group column of my dataset, and then also gathered all of the feature set, which is basically all of the columns in my dataset, all except but the. And now I've split my dataset into the training and test set, giving my test size 20% of my dataset and the training set having 80% of my data. And after that, I've created an instance of the decision tree classifier, and then I've trained the classifier on the training data. After training, I've used the model to make predictions on the first 5 samples in the training data. These are the output of the predicted class labels for the first 5 samples. After that, I've also used the trained decision tree classifier to predict the class labels for the first 5 samples in the test data. To ensure that no testing data will leak into the preprocessing and training, I've also made a machine learning pipeline to do the same process. So first, I've created a pipeline for imputing missing data using a simple imputer and make pipeline functions, where any missing values will be replaced by the median value of the respective column. After making the imputation pipeline, I've combined it with the classifier to create a pipeline object that will first impute missing values in the dataset using the median strategy and then apply the classifier to the transformed data. I've then trained the pipeline on to the training data. To evaluate how well my machine learning model did, I've created a confusion matrix that will display how well the pipeline will make predictions on the testing data and comparing them with the true labels. And here is the result. We can see that the model has an accuracy of 0.9, which means that the model correctly predicted 90% of the instances in the test data, and it also has a balanced accuracy of 0.883, indicating that the model achieved an 88.3% correct classification rate across all classes in the dataset. Both metrics indicate that the model performs well. And having a balanced accuracy, nearly the same value as the accuracy tells us that the model is not biased towards predicting one group in our dataset. After that, I've used the graph-based library in order to visualize the model. And here is the render on PDF file. We can see that the tree goes very deep and that some leaf node contains only 1 or 2 samples like guinea, like here, and here. There's lots of them. This function shows the importance of different features for the classifier, being that CDR or clinical dementia rating, having the highest importance with a score of 0.666, indicating that this feature is the most influential in making decisions in the model. After CDR, we can see that age has the second most important feature with a score of 0.116. Both of these features, CDR and age, has the highest score out of all the features. And that two features, MR delay and the gender, has a very low importance in the classification decisions of the model. Looking at my decision tree, I can tell that overfitting is an issue. And this is because the decision of the tree go very deep and some leaf nodes contain only one or two samples. Looking at the importances of the features, we can also see that CDR having a very high importance while the other features have very low indicates overfitting in my model. However, bias is not an issue as looking at the metric scores. We can see that the accuracy and the balance accuracy are both high and that they're pretty much within range of each other. I will also not be using the principal component analysis for my decision tree just because my dataset contains only 12 features and it is not necessary. To solve the issue of overfitting in my model, I've then created the decision tree, an instance of the decision tree classifier, but with specific hyperparameters. These hyperparameters are the maximum depth of the tree and the minimum number of samples there are in each leaf. So for each hyperparameter, I've given it a range of different values, and so far, giving the maximum depth a value of 5 and the mean samples per leaf a value of 10 gave me the highest metric scores or accuracy and balance accuracy scores for my model. So using those values, I get an accuracy of 0.967 and 0.974. I have also automated this entire process of trying different combinations of values for my hyperparameters, and I've given the max depth a list of values ranging from 1 to 15 and the mean samples per leaf range of values from 1 to 15 as well. And doing this grid search, it has given me the best balance accuracy of 0.9 and the parameters of max depth of being equal to 1 and the mean samples per leaf being equal to 1 to be the best score, which is interesting because when I manually did this process, I had gotten a balance accuracy score of 0.974, which is higher than what the automated process had given. It is also interesting to note that the parameter that was given to have the best score only contains one sample per leaf, which initially caused overfitting for me. So having this values for the hyperparameters is very interesting. Nonetheless, here is the summary of the cross-validation results in a data frame. And now I've selected the best performing pipeline found during the grid search and test out the model on the test data, which it hasn't seen yet. And looking at the metric scores, we can see that the model correctly predicted 96.7% of the instances in the test data, and it has a balanced accuracy score of 0.974, which tells us that this model did good, which interesting. Though thinking about it now, I think one of the main reasons why overfitting is an issue in my model is because of the number of entries there are in my dataset. My dataset only contained 150